Hi everyone and welcome back to chemistry. This is Mrs. Hutchinson and today we're going to continue discussing matter and change, but today we're really going to focus on the classification of matter. So really, how do we classify matter? How do we classify the stuff around us? Well, we have several different ways. The first way is to just simply classify things as mixtures. Well, what is a mixture? A mixture is composed of different parts that are physically combined. What do we mean by that? Well, what do we mean is that we had to do something to put them together physically. So, a homogeneous mixture, if you want to think about it this way, let's think about the prefix homo. Prefix homo means the same. So, if we have a homogeneous mixture, that means that it is the same throughout, consistent throughout, uniform throughout. So, a homogeneous mixture is the same throughout. Now, what is an example? An example would be our salt water, which we have right over here in our beaker. Bam. So, now, how do we know that salt water is a homogeneous mixture? Well, it's basically a mixture because we had to physically combine the salt and the water together. We had to put the salt into the water itself and then stir it around. That is a physical combination, and because if you remember from our prior video, that when something is physically combined, you can get those substances back the way that they were prior to the combination. In this instance, salt water, the way that we just simply separate them would be to boil off the water, and we'd be left with our salt and our water separate from one another. Now, again, what makes this homogeneous is the fact that it's the same throughout. Now, you see this little term over here, solution. Solution is just a term that we use as chemists and will be using for the rest of the year to talk about homogeneous mixtures. When we talk about solutions, typically you mean that something is now dissolved in water. So when something is dissolved in water, it's going to create a homogeneous mixture. Okay. So now, let's talk about heterogeneous mixtures. So, heterogeneous mixtures, if we take a look at our prefix hetero, we mean different. So, heterogeneous mixtures are not the same throughout. They're not uniform. They're typically often very cloudy. They settle upon standing. And usually you can use a filter to separate them. So our prime example would be this beaker of sand and water. So, if you take a beaker and you fill it partway with sand and then you fill it with water, you'll notice that you have layers. We have a layer of sand here at the bottom because it's more dense, and then we have a layer of water on top. So one thing you want to really look for a heterogeneous mixture would be to look for layers. That would mean that it's different throughout. What we mean by that is if we look at the bottom, it's not the same here as it is throughout the rest of the beaker. That's what we mean in terms of heterogeneous mixtures. If you were to stir this beaker, all of that sand would be so cloudy. It would cause the beaker to be insanely cloudy. That's what we mean by often cloudy. They settle upon standing. Basically, how did I get this beaker here, or how did this person get this beaker? You stirred up the sand, and then you just let it settle overnight, and you get these nice layers. When we can use a filter to separate, we just pour it through a piece of filter paper. Sand will be left on top. Water will flow right through. So that is a physical separation that we can use to separate heterogeneous mixtures. Now, things that you want to think about in terms of heterogeneous mixtures. Well, they can use a filter to separate from one another, meaning the sand from the water, but you can't use a filter to separate the salt from the water. Because if you do, that salt water, which is dissolved, is just going to simply go right through the filter paper. So, really want to think about the methods that we can use to separate heterogeneous versus homogeneous mixtures. Mixtures themselves are not governed by this law known as the law of definite proportions. Now, what does this law state? It's a pretty explicit statement. It states that a chemical compound always contains exactly the same proportion of elements by mass. What we mean by that is that H2O here in America, in the US of A, is the same as water in China. And I know many of you may be thinking, like, well, if I go to China, I have to boil my water. If I go to Mexico, I have to boil my water. I'm talking about pure water, distilled water. It's the same in the US as it is in China or Mexico throughout the entire world. The law of definite proportions states that for every molecule of water, we're going to have 2 hydrogens and 1 oxygen. That's the law of definite proportions. The exact same proportion of elements by mass. It's a 2-to-1 ratio. That's what we're talking about. Mixtures, however, are not governed by this particular law simply because, well, they're not uniform throughout. They're not consistent. You might have a 5% solution of salt water. You might have a 50-50% ratio of sand to water. It all depends on how strong you want to make those mixtures. So they're not going to be consistent throughout the world. They're actually not even going to be consistent from one lab to the next. That's why they're not governed by the law of definite proportions. Mixtures can be separated by physical means. So filtration is a physical mean, but remember, heterogeneous mixtures are the only ones that can be filtered, because if you try to filter salt water, it's not going to work. I guarantee you. So if you think it's going to work, go ahead and try it, and then boil off the water and see if you have any salt left. But filtration only works for heterogeneous mixtures where you can have those layers that you can physically separate. Evaporation works for both. Distillation, which, remember, it separates by boiling point. Decanting means that you can just pour off the top of that liquid. That works for heterogeneous mixtures. Crystallization, and of course magnetism. And the major thing that you really want to note is that for mixtures, because we can separate them physically, we don't have to do any kind of reaction to get them back to where we started, they don't combine chemically. If they combine chemically, we would have to go through some kind of chemical reaction to separate them from one another. So now that we talked about mixtures and we got them out of the way, let's talk a little bit about pure substances. What is a pure substance? Pure substances are matter that's composed of parts which are identical in properties and composition. In other words, we're talking about our elements and our compounds. So I'm sure you've heard about both elements and compounds. By the way, my abbreviation for compounds is CMPD. I get pretty lazy, so just so you know. So we're talking about elements and compounds when we're talking about pure substances. The first one's pretty simple. What is an element? It's basically one and only one kind of atom is present. So if we have a pure element, which is a pure substance, we're talking about just one element on the periodic table. All atoms are identical. They can't be broken down in any way, shape, or form. Of course, I will tell you later that this one's kind of a lie. This one's also kind of a lie. But it's the simplest kind of matter. We will clarify those later. But elements are the simplest form of matter that cannot be broken down at all for the time being. And where do we find them all? Well, it's kind of trivial if you want to think about it. But on the periodic table of, well, I don't know, elements. Here we go. There are 118 of them. So any of these are elements. My favorite one being iridium. Of course, we've got potassium, we've got copper, we've got vanadium. They just go on. I could list all 118. I don't know all 118 off the top of my head. These ones get a little tricky down here. But I do know quite a few of them. So a pure substance would be an example of a pure substance is an element. So one and only one kind of atom present. When we get to the end of this video, hopefully it'll make a little bit more sense as to what is what. So now let's talk about a compound. Well, what is a compound? It requires a minimum of 2 atoms bonded together per piece of substance. When we say bonded, what that means is that they're chemically combined. I ran out of room. There we go. Bam. Chemically combined. So, elements that are chemically combined are known as a compound, which means since they're chemically combined, they have to be chemically separated. The characteristics that we look for would be to look for 2 or more elements themselves. So, the first thing that we want to check out is to see, do we have new properties? Well, here's our example. We have copper sulfate. It's copper sulfate pentahydrate, but we're going to leave off the water for now. So we've got CuSO4. That means in this compound, copper sulfate, we've got copper, sulfur, and oxygen. So taking a look at these, here's our copper. It's a nice orange color. It's actually, some might say, copper color. We've got sulfur, which is a nice yellow color. And we've got oxygen, which is kind of hard to find a picture of because it's colorless. So I found the tanks. But if we look at all of those, we've got orange colors, yellow colored, and colorless. And when we add them all together, we form this bright, bright blue crystal known as copper sulfate. So when we combine those 3 elements, we can notice just by simply looking at the colors that we now have a chemical change. That would be a compound because it is chemically combined. The color itself is just indicative of that. If we take a look at the next one, this one's actually kind of interesting if you really want to get into this stuff. This is where I find chemistry so incredibly awesome. So sodium chloride. Everybody's heard of sodium chloride. It happens to be table salt. If I can get that to right. There we go. So table salt. In sodium chloride, which is also known as NaCl, we have sodium and we have chlorine. So what is sodium? Sodium is a soft silver-colored metal. It reacts very violently with water, which we saw in our prior video. So sodium is not something that we really want to be around when it's in its pure substance, its pure form. Chlorine, same idea. It's a poisonous yellow-green gas. It has a very sharp and distinct odor, and it was used during World War I. If we take a look at this right here, it's a yellow-green gas that has a strong kind of bleach-like odor. Basically, what it's going to cause you to do is it's going to react with the water in your lungs, forming a very strong hydrochloric acid that could cause death at 100 parts per million. So pretty readily it's going to cause some kind of death, some kind of major issues. And in World War I, chlorine was devastating as troops were initially very unequipped to deal with it. So both sodium, which is explosive with water, and chlorine, which is deadly when combined with water, those are 2 substances that we really don't want to deal with when they're in their pure forms. However, if we take a look at this, when they're combined, we get table salt, which as humans, we need. It is essential to our life because it has to regulate the water content in our bodies. If we didn't have salt, we wouldn't know how to deal with the excess water that we are required to drink to stay alive. So we need salt. So it's weird. You get a deadly substance plus a deadly substance yielding a substance that is essential to life. Welcome to chemistry. It doesn't really make much sense. But interesting nonetheless. Compounds have definite ratios. What do I mean by that? Well, if you take a look, H2O and H2O2, they've got exact ratios that will never change throughout the whole world. So whenever you're looking at water, you're going to have 2 hydrogens and 1 oxygen. Whenever you're looking at H2O2, which is hydrogen peroxide, you have 2 hydrogens and 2 oxygens. Those are 2 different compounds because they're made up of 2 different elements that have 2 different ratios. Things you want to think about: water, this one over here, you need to stay alive. You drink any H2O2 or too much H2O2, it's not an ideal situation for you. It's kind of poisonous. The hydrogen peroxide that you use at home to clean cuts is only 3% hydrogen peroxide. 30% hydrogen peroxide, which some labs have, it's quite an oxidizer. It's quite dangerous. So just that one measly oxygen makes all the difference here. They're governed by the law of definite proportions, basically because, well, H2O is H2O is H2O. Wherever you are in the world, going to have the same ratio, as long as you're talking about pure H2O. And they cannot be separated or purified further by any physical means. Meaning, if you wanted to separate the hydrogen from oxygen, so if you wanted to perform this kind of reaction to separate those substances, you would have to perform a chemical reaction. You can't just simply put H2O through a strainer, water through a filter paper, and expect the hydrogen and the oxygen to be separated. No, because it was chemically combined, it has to be chemically separated. So here's a nice little flow chart to kind of help us figure out what's going on in terms of, well, what matter are we looking at? First question that we're looking at, that we would ask ourselves when we're looking at any piece of matter is it uniform throughout? Meaning, does it have layers? Like onions. Or parfaits, because, well, everybody loves parfaits. But anyway, is it uniform throughout? So does it have layers? If it does have layers, that means that it is not uniform throughout. That means that we're going to be talking about a heterogeneous mixture. So we're going to definitely have layers visible here for a heterogeneous mixture. If it is uniform throughout, meaning no layers, we're looking at something that is homogeneous. So there are further classifications that we could talk about for heterogeneous mixtures, but for our purposes, we're just going to leave it as if it's got layers and it was physically combined, well, it's a heterogeneous mixture. If it does not have layers, we're looking at something homogeneous. Now we can branch off from there. Can it be separated by physical means? Meaning, can we use filter paper to separate it? Can we use distillation to separate it? Evaporation to separate it? If it can be separated by physical means, that means that it was combined using physical means. That means that we are talking about a homogeneous mixture or a solution. So, if it can be separated by physical means, it has to be combined using physical means. If it cannot be separated by physical means, that means we're talking about a pure substance. Because those substances were combined chemically, if they were combined at all. Last but not least, can it be chemically decomposed? Meaning, can it be broken down chemically? So, if we look at our elements, they're the smallest form of matter, simplest form. They cannot be broken down in any way, shape, or form. Therefore, they can't be chemically decomposed. It's an element. If it can be chemically decomposed, that means that it was chemically combined. That means that we were talking about a compound. So hopefully this flowchart kind of helps you. If this is a little too much for you to take in, you can pause it, rewind it, and look at it again. Hopefully it'll start to sink in. Well, we will discuss it in class when we go over this particular video. So now, you have this worksheet. It's our classification of matter worksheet. Yes, with your scientific senses, observe and or use your prior knowledge asked about the following types of matter and write the correct classification or properties asked of you below. So let's think about this. Copper wire. You probably know what copper wire looks like. It's, well, copper colored. So the thing is, let's think about this. Is it uniform throughout, or is it uniform throughout, yes or no? Yes, it is uniform throughout. So that means that we're talking about something that is homogeneous. So since we're talking about something that is homogeneous, can copper wire be physically separated? And when I say physically separated, I mean, can the atoms in there be physically separated? Because, well, what's in copper wire? Just copper. So can those copper atoms be physically separated? No. So since it cannot be physically separated, we're not talking about a mixture. So now, we're talking about, well, we have to talk about a pure substance. It's either a pure substance or a mixture. Since we determined that it can't be physically separated at the atomic level, we're talking about a pure substance. So now that we've at least canceled out heterogeneous, homogeneous mixtures, we're looking at elements or compounds. Is our copper wire, can that be chemically decomposed? Can it be chemically broken down? Meaning, is this found on the periodic table by itself, or is it made up of multiple atoms on the periodic table? Well, it's made up of just simply copper, therefore it is an element. And explain how we came to our conclusion. We found it on the periodic table. So go ahead and take a look at the rest of these on here. Take your time. It might be a little tricky. I promise you'll get a little better at it as we go. They say practice makes perfect. I say practice makes better. It's very difficult to be perfect. So go ahead and try that, and we will discuss this video for our next class. And I will see you next video.